Hello everyone, my name is Thompson and I'm about to present a research study that was titled Improving Localization and Measurements of M Waves Using High-Density Surface Electromyography. The problem that was being studied in this research was crosstalk, which is the interface of signals from adjacent muscles, which often limits the effectiveness of traditional surface EMG. The study evaluates high-density surface EMG combined with special filters to isolate these signals more effectively. The research is significant because it provides better tools for assessing neurological damage, such as stroke or spinal cord injury, and for improving the control of prosthetics. The literature evaluation for this study is thorough, citing 28 separate sources to ground this research in established science. These references are directly relevant to the research questions, covering topics from motor unit recruitment and stroke prognosis to modern electrode density. The researchers recruited 5 right-handed able-bodied volunteers between the ages of 24 and 40 for their physiological validation. Clear isolation criteria was established. Participants had to be medically stable with no neurological impairments or joint deformities. Subject safety and ethical standards were prioritized, and the study received full approval from the Carnegie Mellon University Institutional Review Board. The methodology involved placing 64 electrode grids on the forearm, recording at a high frequency of 4,000 Hz. Peripheral nerve stimulation was used to selectively activate specific muscle groups in a controlled way. A critical part of the design was using ultrasound imaging to confirm exactly which muscle boundaries were located beneath the electrodes. This multimodal approach allowed the researchers to cross-reference electrical signals with anatomical ground truths. Data analysis focused on comparing 3 types of montages: monopolar, the control, bipolar, and tripolar. Researchers used linear correlation coefficients between electrodes to objectively measure the amount of crosstalk present. They also calculated amplitude decay, which measures how quickly a signal disappears as you move away from the target muscle source. Over 65,000 observations were aggregated using cumulative distribution functions to ensure the findings were statistically robust. The results showed that the tripolar montage was significantly better at minimizing crosstalk than the others. In the tripolar mode, the signal decayed by 51.1%, just one electrode away from the source, compared to only 10.3% in the monopolar mode. The tripolar filter effectively reduced crosstalk to negligible levels at distances greater than 2.5 centimeters. If you look at the heat maps, you'll see that special filtering allowed researchers to visualize action potential propagation that was completely masked in the monopolar mode. The authors interpreted these results to show that without special filtering, recruitment curves are distorted because they falsely include activity from nearby muscles. This correlation is essential for accurately measuring how muscles respond to different levels of stimulation. However, there are limitations. Tripolar filters can remove some target muscle information, and the study did not specifically address crosstalk from deep muscles. So, significance and conclusion. The study's significance lies in the combination of anatomical and electrical data for more precise and muscle mapping. This framework could lead to more accurate diagnostic tools and more intuitive prosthetic control systems. Finally, the work is highly replicable, as the authors shared their MATLAB processing code on GitHub and made their source data openly available. Thank you for listening.